We're going to look at our first lesson in ligand substitution reactions, and we're going to look at substitution by monodentate ligands. Remember that word monodentate literally means one teeth or one toothed, so that's only ligands that can have only one lone pair that is able to form a dative covalent bond. So there are a few things that we need to remind ourselves of before we can move on with this. So it might be that you want to draw a diagram of octahedral geometry and tetrahedral geometry and define these two by pausing the video now, and then I'll go over them. So an octahedral geometry, if we look at our aqueous copper ions as an example, so we have got 6 water ligands. The bond angle would be 90 degrees. I haven't drawn these in 3 dimensions, but these 4 ligands here would be in the flat of the plane, and these 2 would be in the axial positions. Tetrahedral, we're going to see an example of a tetrahedral complex today. If I just draw this one in 3 dimensions. So we've got lone pairs from the chloride ions forming dative covalent bonds, so we've got arrows on those there to the copper 2+ ion, and the bond angle here would be 109.5 degrees. Definition of coordination number is simply the number of dative covalent bonds in the complex, or dative covalent bonds to the transition metal ion. So the coordination number of this geometry would be 6. 1, 2, 3, 4, 5, 6 dative covalent bonds, and the coordination number of this geometry here would be 4. There are 4 dative covalent bonds. Lone pair, arrow, lone pair, arrow, lone pair, arrow. A ligand is a species with a lone pair able to form a dative covalent bond to a transition metal ion. So we're going to summarise our 3 types of substitution reactions first of all. They're complete substitution with no change in coordination number, incomplete substitution with no change in coordination number, and complete substitution with a change in coordination number. There are some others as well, but those are the 3 that we need to know about. So I'm just going to think in general terms first of all. So if I were to think about the complex MX6, so I've got X I'm just using to represent any ligand. If I were to react that with 6 of a different ligand, then in this case, which I'm using L to represent, then all 6 of the X's would be replaced by 6 L's. So we'd end up with the complex ML6, and the 6 X's that were in the complex with the metal ion would be displaced or kicked out. You'll see these in real examples in a minute. Don't forget that these are likely to have a charge as well, a positive charge. Incomplete substitution with no change in coordination number. Well, we start with our same complex again, and this time we're going to have less than 6 of the X's or as L's being replaced. So in this case I'm just reacting 4 L's. So this time we would have a complex that still had 2 of the X ligands but now has 4 L ligands, and we would displace, kick out, remove 4 of those X's. So let's just think about exactly what we've done here. We've got 6 ligands, therefore we're going to have a coordination number of 6. We've reacted that with 6 L's, which are also monodentate ligands. They have kicked out or displaced all of the X ligands, so they're on their own, no longer in the complex, and replaced them in the complex. The coordination number of this is also going to be 6 because there's 6 ligands. Similarly here, 6 ligands, therefore 6 dative covalent bonds if they're monodentate, and therefore a coordination number of 6. But this time we've only reacted it with 4 of the new type of ligand, of the L ligand. So that has displaced, sorry, I just realised I made a mistake there, that should be 2 X's. So that's going to kick out, no, sorry, that was right. That's going to kick out 4 of the X's. So we've only got 2 of them left, and then it's going to replace those 4 that have been kicked out by the L's. Apologies about that mistake, I just second guessed myself then. Now this has got 1, 2, 3, 4, 5, 6 ligands. They're all monodentate, so there's going to be 6 dative covalent bonds, therefore it has a coordination number of 6. We can have complete substitution with a change in coordination number. So this time, here's our complex with 6 ligands. We're going to react it with four ligands. I'm actually going to give these a different symbol, and I'm going to give the symbol of Y just to make sure they're different from the ones that I used up here. Now this occurs if the Y is significantly larger than the X ligands. So all 6 of the X ligands have been displaced, removed, and then we have a complex now that has just got 4 ligands. So we had a coordination number of 6 here, we've gone down to a coordination number of 4 here because we've only got 4 monodentate ligands. Let's have a look at some real examples. So 3 examples, the first 2 of which you have to know for this course. So you need to know the colour changes and you need to know what's happening. So aqueous copper 2 sulfate with concentrated hydrochloric acid. Let's think about what we've got here first of all. From previous sessions, we should have hopefully realised that the copper 2 sulfate, because it's an aqueous copper 2 sulfate, what we're particularly interested in is the copper 2. The sulfate ions will be spectator ions. They will be in the aqueous solution, but they have nothing to do with the reaction at all. So what we've actually got here is the aqueous copper 2 plus complex. So we've got a 2 plus here because the copper has a 2 plus, copper 2, and the 6 water ligands are neutral, so the complex itself has that 2 plus charge. How do I know it's got 6 water ligands? Every single transition metal aqueous ion in solution is the metal and 6 water ligands like this. Now concentrated hydrochloric acid in the case of transition metals is producing Cl- ions as a ligand. So we're going to react with 4 chloride ligands. The reason being is the chloride ligands are much larger than the water ligands, so they're going to displace all 6 water ligands, and we're going to get that last case example of a reaction where we have a change, complete substitution with a change in coordination number. So what happens now is we have CuCl4 in the complex, and I'll draw these as diagrams in a minute, and it's kicked out all 6 water ligands. We had a coordination number of 6 here, we've gone down to a coordination number of 4 here. Why has that happened? These are very large ligands, and only 4 can fit around the complex, sorry, complex ion. So that's why that's happened there. So this would be that octahedral geometry that we saw earlier. Now there's one thing that we haven't done, sorry, not octahedral, this tetrahedral geometry that we saw earlier. This one thing we haven't done is work out the charge on the complex. The copper 2 plus is still 2 plus, it hasn't changed oxidation state. We've got 4 Cl minus ions, so overall the charge on that complex is going to be 2 minus. We also need to know the colour change. This is a blue solution and it changes to a yellow-green solution. So these are colour changes that you have to know. Let's have a look at example number 2, reaction of aqueous copper 2 chloride with excess concentrated ammonia. Remember as last time, aqueous copper 2 chloride, we're interested in the aqueous copper 2 ions. The chloride ions are going to be in spectator ions in solution. They don't form complexes. The reason, obviously, we've just had an example where we've had chloride ions. We had with concentrated hydrochloric acid, we've got a huge excess of chloride ions. With aqueous copper 2 chloride, we've got an equal amount, or 2 times stoichiometric quantity. So we would need significantly greater chloride ions than would be provided by this in order for a substitution to take place. So let's draw our complex, hexa aqua copper 2 plus complex. Now this is an unusual reaction, and there's no way of explaining it really at A level. I can explain some of it to you when we get back if you want, but it reacts with 4 ammonias, but it is an incomplete substitution with no change in coordination number. So what happens here is we still have 2 water ligands, but we have 4 ammonia ligands, and we displace or kick out 4 waters. How do I know that? I've reacted it with 4 ammonias. I've still got 2 waters in the complex, therefore I've got to get rid of 4 waters. So this is just something we have to know. It's unusual because most of these reactions with ammonia are in fact complete, and you'll see on the next one, but this is just an exception. We need to know the colour change for this. This is a blue solution, and this is a royal blue or deep blue solution, and we need to know those colour changes. If we wanted to draw a diagram of this Cu2 plus, we in fact have the 2 water ligands in the axial positions, and then our 4 ammonia ligands around here, or 8. Okay, so reaction number 3 is similar to this one up here, but this time this is how most of these reactions actually occur. So cobalt 2 sulfate, aqueous cobalt 2 sulfate. What are we interested in? Just the cobalt 2. So that's our complex, and this time we react with 6 ammonia ligands, and all 6 water ligands have been displaced or kicked out. Therefore we have 6 H2Os at the end. This isn't a colour change we need to know, but there's something interesting that we do need to know about it. This is red, and then we end up with a straw yellow solution at the end. However, if you if this is left as an open test tube in the air, what actually happens is we end up with a red-brown solution. And this is something that often happens with certain transition metal ions. So if we've left this complex, it's red-brown solution. What's happened to it is this. There's no change, so it's not a ligand substitution reaction, it's still this, but it's now a 3+ charge. So the ammonia has no charge. So what's happened in coming from here to here is it has oxidized, or the transition metal ion has oxidized in air. So the O2 has caused that to happen. So it isn't a ligand substitution reaction, it's just oxidized in air. So there are 6 questions I want you to have a go at. I will put the first 3 up if you want to pause the video and have a go at them. And then here's the next 3 if you want to pause the video and have a go at those. And then I'm very quickly going to go through the answers and just elaborate on a few points as we go through it. If you don't want to listen to me going through the answers, then right at the end of the video I will put the completed sheet, and I'll leave it there for a few seconds so you can pause it and have a go at it. Aqueous iron 2 sulfate, FeH2O 6 2+ with concentrated hydrochloric acid. Chloride ions are large ligands, so they're going to are only going to be able to fit 4 around there. So FeCl4 2- charge, because we've got a 2+ on the ion and 4 chloride ligands, which adds up to 2+ and 4-, therefore it's 2- overall. In terms of colour change, you don't need to know it, but it is actually something this particular exam board often like to include some sort of things that you don't necessarily know or haven't come across before, so it's worth us just being aware of them. So this is a green solution and this is a yellow solution. Chromium, aqueous chromium 3 chloride with an excess of concentrated ammonia. So aqueous chromium 3 is in fact this, and it's reacting with an excess of ammonia, concentrated ammonia. This cobalt 1 is not like the chromium. I've just realised that should be CrH2O6. This isn't like the unusual one, copper. So all 6 water ligands are substituted. Aqueous iron 2 ions with concentrated hydrochloric acid. So aqueous iron 2 ions. So we've got Fe H2O6 3+ with 4 Cl- ions. We're going to substitute all, it's a complete substitution, but we get a change in coordination number. So we've gone from 6 to 4, and 6 waters have been displaced. In terms of the charge, it's a 3+ ion, and we've got 4 Cl-, so that has a 1- charge overall. This tends to be an orange solution. There are debates about how people interpret that particular colour, which we'll talk about later in future lessons. And then this is also actually unusually a yellow solution, but a slightly different colour yellow solution compared to the previous one. In terms of the type of reaction has taken place, complete substitution with a change in coordination number, complete substitution with no change in coordination number, complete substitution with a change in coordination number. So reaction of aqueous Cu2+ ions with an excess of concentrated ammonia. So the product is this going to be this unusual product where we've got 2 water ligands because the substitution is incomplete, and then 4 ammonia ligands. Reaction aqueous copper 2+ ions with hydrochloric acid. Cu2+, Cl-, Cl-, Cl-. I haven't drawn these in 3 dimensions, either of them, so it would be worth me putting the bond angles in and also stating that I know that that is tetrahedral and I know that that is octahedral. And then aqueous iron 2 is a green coloured solution which, when left in air, turns orange. So we start with the green coloured solution, which is Fe H2O6 times. It's going to be oxidized by the oxygen present in the air. It's Fe H2O6 times 3+. Thank you very much.